Hello, welcome to the week 2 asynchronous video for information visualization. And this time we're going to talk about marks and channels. So what is this idea of marks and channels? Well, remember that last time we talked about the nested model where we differentiated between the domain situation, the abstraction level for data and tasks, and then the idioms for visual encoding and interaction, and then finally the algorithm level. So let's take a minute to think about this idiom level of how do we systematically analyze the structure of an idiom, specifically a visual encoding idiom. So let's take a few things I'm sure you've seen before, bar charts, scatter plots. What is going on here? How can we think about it systematically? So we want to use the idea of marks and channels. A mark is going to represent an item or node, or it could represent a link. And a mark is a way to change the appearance of those marks based on some attribute values. So let's dive in. So marks, think of these as really basic geometric elements where every sort of mark, literally think about making ink happen on a page, every mark is going to represent a thing, an item. These could be points, lines, interlocking areas. It's also possible to have a 3D mark, a volume, although we're not going to use that much, especially in an information context, information visualization context like we're doing in this class. Now, marks don't just have to be items or nodes. They could also be links. Remember, we could have node link networks as a data type that we talked about last time as well. So in this case, a mark might be representing a link, and it could be what we'll call a containment mark, enclosure, like we see on the left side here. Here's where you see this, what's called a bubble set. It's actually enclosing a bunch of those points in an outline, an enclosure. Or another way, and maybe a more familiar way, is to use connection. You can actually draw a link between two nodes to indicate that these things are related. And this is what you see here in a node link graph layout. Um, so this is another way to explicitly indicate the relationship. And in this case, those line marks are showing that two nodes are linked together. I'll mention containment actually can have a hierarchical nesting structure. For those of you who've seen Venn diagrams, there is a sort of generalization of them called Euler diagrams, and some visualization folks have even gone deeper in and built some visualization idioms really built on the idea of nested hierarchical multi-level containment. And we'll come back and we'll see more about this in the week that we talk about networks. This is just to give you a flavor of how containment marks could be used. So let's go back to channels. The idea was the channels are controlling the appearance of marks. And what we want to do is control that appearance in a way that is proportional to or somehow based on attribute values. Now, you'll see if you read other sources, people give these a lot of different names. They all mean the same thing. Visual channels, visual variables, retinal channels, visual dimensions. These are all different, just synonyms for the same basic idea. We're going to encode information about attributes in some way that the visual system can respond to. So that could be spatial position, horizontal or vertical, or both at once. We could color code things. We could shape code. We could even orientation code with the amount of tilt. We could size code, we could have a length coding or an area coding, even a volume coding, although again, we're not going to use that too much in an InfoVis context. Okay, so, right, we've now seen these marks that are these geometric primitives. We've seen these channels that can control the appearance of these marks. So the thing to know though is channels are not all created equal. They have really different properties. So the type of information and the amount that can be conveyed to the human perceptual system is definitely different across the different visual channels. So let's go back. We had these examples. Let's actually try analyzing them according to these ideas of marks and channels. So on the left here with the bar chart, what we've got is vertical position. And there's a single attribute that we're encoding, and we're encoding it with a line mark. And the vertical position, the height of the line mark, is encoding our attribute. What else? We could have both vertical and horizontal position. In this case, we have to switch from a line mark to a point mark so that we can actually see that without too much clutter. But we could keep going, right? We could add another channel. Here we could add color coding. So we're still using point marks, but we've added another channel. And then finally, we're adding even a fourth channel. We're size coding. Sometimes people call these bubble charts, or bubble plots. And so now we've got multiple visual channels being used. So one for each of four quantitative attributes, or uh, in some cases, not so quantitative, as in the color. We'll get to that in just a minute. Now, it doesn't just have to be one channel per attribute. You could use multiple channels to encode the same attribute. Here we're length coding by something, but we're also luminance coding by that. In fact, we sorted according to this attribute value as well. So we've got length and position and luminance all encoding the same thing. So that sends a much stronger message. But also the downside is it uses up these channels. Now we can't use them on other attributes. So you can redundantly code same attribute with multiple channels, but then of course you use it up. So as with many other things in visualization, it's a trade-off. Now, another way to think about marks is, there's a sort of mathematical view, which is that it's a geometric primitive that's either 0 or 1 or 2-dimensional. But there's a helpful way to think about it when we're analyzing visual encodings, which is how many constraints are there on that mark? So in this constraint point of view, the type of the mark really constrains what else you could encode. So if you've got a point mark, the question is, well, could you size code that point mark? Could you shape code it? And the answer is yes, there are 0 constraints. So you could, you can position code a point, you can size code it, you can shape code it. It's very unconstrained. What about these line marks? Well, there's a constraint already. A line mark sort of intrinsically is encoding an attribute with the length. Um, so that's in some sense used up. You could still size code the other way. So you could have a second attribute that you're using to width code your line. Um, but in contrast, what about these interlocking area marks? So area marks, they're completely constrained. You can't length code or width code an area mark. Its area, its exact boundary is already specified. So you can't size or shape code area marks. In fact, it's useful to think about these as interlocking, that the size and the shape and the position are all specified. And we'll be talking much more about then how to visually encode with these marks. They're often algorithmically generated, or they come from something like a geographic shape where it's given as part of the spatial data. So the quick check about is something, a point marker, a line marker, an area mark is, could you size code another attribute? And if you could do any kind of size coding you want, it's probably a point mark. If you're constrained in one dimension but not the other, it's probably a line mark. And if you're completely constrained, so you can't really change the size and the shape or even the position, then you're probably dealing with one of these interlocking area marks. And we'll get some practice on these coming up. Not today in the asynchronous lecture, but when we next meet for the synchronous class, we'll work through some of these with the in-class exercises. Let me just make one final remark before we leave the subject of marks. We're going to come back to more complex things later. So right now, this kind of mark and channel decomposition of a visual encoding, this is based on the assumption that there is one mark per item and that there's only one single view. Later, we're going to relax these assumptions. We're going to talk about some ways of having multiple marks, of having multiple views. But for now, we're just thinking of a world where there's one mark per item or per link. And so we'll think about multiple marks in something we'll call a glyph, or the idea that maybe some items don't even have a mark once we get to things like aggregation and filtering. But that's for later classes. Right now, we're thinking about the relatively simple case. So we've been talking about marks, but let's come back to channels. How do you know when to use which channel? And there's two really big principles. The expressiveness principle is about matching the channel type to the data type. And the effectiveness principle is about recognizing that some channels are better than others, and that you want to be careful about deciding which channel to use and which channels to map to which attributes. So we've already seen the idea that there's a lot of channels. But we've also seen this idea that they're not all created equal. So what are the major ways that we can distinguish them? Well, it's no coincidence that I've really got these two different columns here. Everything on the left are what we're going to call magnitude channels. And these are a good match with ordered attributes. They actually convey to your perceptual system information about magnitude, right? So questions like how much, which rank. So remember that for attributes, we had ordered attributes. And so there's a bunch of these. So position, length, tilt. You could say how long is something? How tilted is it? How big is it? How dark is it? How saturated is the color? How curvy is it? So these are all intrinsically communicated to your perceptual system as magnitude. So they're very good for answering questions like how much. Now, in contrast, the ones on the right side, the identity channels, these are a really good match for categorical attributes. These really help answer questions about what, what color is that? What motion is that? What shape is that? What region is that? So there's this real distinction between how much perceptual channels and what perceptual channels. Um, and the key thing with the expressiveness principles is you've got to match these up. What can go wrong if you don't? If you're trying to convey um, information about magnitude using a magnitude channel for an attribute that's not ordered, well, you might misleadingly communicate something that's not really there in the data. And then the converse is true. What if you have an ordered attribute, but then you use the identity channel to visually encode it? You've just thrown information away. You've lost it. So you have to be careful to not either mislead or lose information. And that's where you really want to think about the expressiveness and make sure that you've got things matched up. Now, what else? It's also not a coincidence that these things are in a vertical order. So there is actually rankings for these channels of their effectiveness, specifically of their accuracy. How accurately can humans perceive these different channels? So we're really good at spatial position. We're, you know, so-so at angle and area. We're really not so good at depth. We can see some grayscale values. We can see some curvature. We're particularly bad at volume estimation. Um, and Likewise for the identity channels, we're really good at noticing which spatial region something is in. We're quite good at color, noticing what color something is. And we can start to see some stuff about motion and shape. Um, So these are all arranged from most effective, most accurate at the top down to least effective at the bottom on both of these sides. One thing I do want you to notice, spatial position is at the very top for both magnitude channels and for identity channels. So that's a really crucial point, is that spatial position is the most highly ranked thing in both the magnitude and the identity side. So that's one reason we're going to spend a lot of time talking about the use of spatial position in this class, is because it is so completely fundamental to how humans perceive visual encodings. So let's talk a little more about channel effectiveness. When we're going to bring up this key idea of accuracy, how precisely can we tell the difference between things that are being visually encoded? How discriminable, how many unique steps can we perceive? How separable, does one channel stomp on another, or are they completely independent? And then pop out, can things actually just jump out at you without effort by using channels? So let's talk about each of these. So fundamentally, there was a huge amount of work in what's called psychophysics, that is, how people respond to sensory phenomena, that's happened over the past, well over 100 years. And S.S. Stevens was one of the pioneers in this area. Um, and after literally decades of work, there's some very firm results that people respond to sensory stimuli according to power laws. and which modality you're responding to, it's going to have a different exponent. So they're always going to be on one of these power law curves, but some of them are in fact perceived very, very accurately, specifically length. It's got that exponent of 1, right? So the sensation as intensity to some value. So length is it's linearly perceived. So you're really, really able to decode length without distortion. Now, some sensory modalities are compressed, like our ability to sense area or depth into the 3D scene or brightness. These are actually compressed, where if you double the sensory stimulus, you do not get double the response. These are the compressed ones. Others are magnified. So notice how they are, above that linear length. Things like color saturation, worse yet, electric shock. Don't worry, that's just a tingling on the fingertips, not anything lethal. But they have in fact tested this stuff, and those are these superlinear responses. So these are really fundamental results from psychophysics. This is not specific to visualization, although we make use of them in visualization. So that's some of the more fundamental theory and so basically how far from the linear case these are is going to determine accuracy. And then people have also done experiments literally of looking at different visual encodings and measuring. In this case, some really fundamental work from Cleveland and McGill was how do people respond to things like, bar charts, pie charts. So basically, really checking what is our ability to decode information that's encoded with spatial position or angle or areas. And the key thing on this graph is it's showing you, in this case, the horizontal axis is the log scaled error, is what are the errors of people when responding to these, and notice how the amount of error increases as we go down in these ranks. So these are following that ranking that I showed you on the previous slide. What we're actually seeing here is how some later work from Hare and Bostock. Bostock, by the way, is the same guy who Hare and Bostock together actually created D3, which you are starting to learn even as we speak. And so this is some nice results where they replicated that Cleveland and McGill work with crowdsourcing on Mechanical Turk and essentially got the same results of there are more errors the further down we go in terms of people being able to decode information that was encoded using these different visual channels. Now, accuracy is not the only thing we have to worry about. What about discriminability? That is, how many usable steps are there, like steps or bins? And the key thing is we want to match this up. So we want to have the number of discriminable bins match up in the channel that are available, match up with the number of levels there are in the attribute. So let's take this example. It's showing telecommunications network traffic in Europe from a number of years ago. And the key thing to notice is line width is it's very effective. We can clearly understand what they mean, which is that some of these flows are larger and some are much smaller. But of course, there's a really limited number of bins with line width. If you make a line too fat, it doesn't even look like a line anymore, right? It just starts looking like some polygon, right? So there's a limit as to how many bins there can be for line width to encode something. So that doesn't mean it's ineffective, but it means if you had something where you were going to try to show 200 different steps, well, then line width is probably not a good choice of channel. So we have to worry about do these match? And we'll be talking more about these as we, particularly about color in later weeks. Now, there's another thing we have to worry about. Can we just keep using channels independently of each other and have everything work out? Sadly, the answer is no. We have to worry about, are these visual encoding channels separable? If the visual channels are separable, we can encode two different things with them, no problem. But if you integrate them together with your visual system in a way that you can't control very well, well, then they can't just independently encode things. So let's look at some examples. Starting on the left, we have the nice case, the easy case where we've got very separable channels. So what have we got here? Well, you can definitely notice that there's a group of points on the left and a group on the right. Easy. And you can also notice that there's blue ones and orange ones. So we've got this situation where we can either attend to the spatial position or we can attend to the color coding. These are fully separable channels. They don't interfere with each other at all. So we really are seeing, we can see either of these two different groups. Now, what happens if we scooch over one to the right and we're color coding, but we're also size coding? So there's a little bit of interference here. I bet everyone is really easily able to see that the large dots are either purple or blue. Um, but it's a little harder to check that with the smaller dots. It's not impossible at all, but it's a little bit harder to notice the blue and the purple as the dots get smaller. And that's because our ability to perceive color decreases with the size of the element. So color perception is very tied to the size of the item we're looking at. Wow. So there's interference between these two channels. A little bit inconvenient. What about this one over to the right, the width and height? Now, what if we said, I know I'm going to width code and one attribute, and independently I'm going to height code another attribute? Sounds great. But what happens when we look at this picture is we don't really see those two groups of two. We see big things and we see little things and we see squished things, right? And the question of whether they're squished in one direction or the other is not as salient to our perceptual system. Because what's happening is your eyes, actually your visual system at a not very conscious level, is actually integrating together the width and the height to perceive area. So even if you're trying to independently length code and width code, your brain is actually really strongly going to have a tendency to just read back out that area. So there's significant interference here. We're not really seeing the two groups of two. We're really more seeing three groups. And now the case on the right, it's the worst case of all. I can tell you that I carefully encoded red and green. There is a high value of red and a low value of red, and there's a high value of green and a low value of green in the color coding of these points. And it doesn't matter what I tell you, that's not what you see. What you see is four different colors. Your perceptual system has intrinsically taken these high and low red and green values and just converted those into a perception of color. So even if you try really hard, you can't see two different groups of two, you just see four groups. So, we'll talk more when we get to color about why you shouldn't try to color code in this way. But the more general point I want you to walk away with is remembering that these channels are not necessarily independent. There's a lot of situations where they have some partial or some significant interference. And so we're going to have to think about that as we discuss visual encoding. There's one more phenomenon I want us to think about, this idea of visual pop-out. So I know that you're watching this asynchronously and we're not all in class together, but I still want you to actually do this along with me. So what I'm going to do is I'm going to say 3, 2, 1, go. And then what I literally want you to say out loud is got it as soon as you actually see the red dot. So let's try this. 3, 2, 1, go. Got it? Okay, I found that red dot. There were a bunch of blue dots, but I found the red dot. All right, let's try this one more time. 3, 2, 1, go. Got it? Okay, so that was our warm up. Not too bad. Let's try it again. 3, 2, 1, go. Got it? So sneakily enough, this is not about color anymore. It's not red versus blue, but it's about dot versus squares, but I could still spot that dot. Let's try that again. Got it? Okay. So of course, what you're noticing is I've got a small number of distractor elements versus a large number. Let's do another final round of this. 3, 2, 1. Got it. Okay. Now, very last one. Are you ready? 3, 2, 1. Got it. So what just happened there? That was pretty quick. on actually both sides, left and right, for those top few. And then on the bottom one, there was a pretty large gap before I was able to actually notice when I had both red and blue dots and squares, somehow it was pretty hard for me to find the red dot. So what's going on here is if you're just looking at something in one channel at once, your visual system's doing something pretty amazing. It's doing parallel processing on any individual channel in a way that's pretty much independent of the number of distractors. It was the same whether I had 100 or 1,000. Even if I, in this case, I had 10 versus 100. If I had 1,000 blue dots and one red dot, I would still be very, very fast at finding that red dot. Um, but once I say red and blue dots and squared, things actually get much slower. And the amount of time it takes me to find that now starts to be a function of the number of distractors. And if I had 1,000 of these, it would have taken me a very long time. So in almost every case, combining these visual channels together means you're no longer able to get that pop-out effect. So this doesn't mean pop-out has no use, but it means you can't just sort of layer it on through many channels at once. So you can do pop-out for basically one thing at a time with a small number of exceptions, and certainly trying to do three at once is not going to fly at all. Now, pop-out is not just for red, red and blue, dots and squares. The way pop-out works is the sort of closer, if you sort of think about a space of possibilities, the closer two things are to each other, the harder they are to tell apart, and the further away, the easier they are. So the dots versus squares is a little bit harder than the colors because that's a filled in dot and a filled in square, and they're pretty close to each other in a sort of conceptual shape space, whereas the red and the blue are more different from each other. Um, so what else can we do pop out with? Actually, quite a few. We can do pop out of, in this case, we're seeing orientation, size, certainly shape, as we already saw, but even subtle things like proximity, um, even stuff like shadow, like the direction of the shadow we can get pop out with, stunningly enough. Now, not everything actually does do pop out. Here's one. Parallel lines, it's actually not something we're able to do this non-attentive processing. We have to actually go through and check are two things perfectly parallel or a little bit inclined. So that's an example of a way to actually visually encode that does not provide pop-out. But there's many, many that do. Okay, what about factors that affect accuracy? We've now sort of talked through a bunch of things. So what do we want to think about? I already showed you in the list of channels that spatial position, especially aligned spatial position or along a common scale, was the most accurately perceived. So that is a factor that affects accuracy. Are things aligned? Are there other distractors? Like we just saw some examples of, red and blue. So the number of distractors can affect your accuracy. The question of whether two marks are aligned can affect your accuracy. Here we see that we've got aligned versus unaligned, or if things are really far from each other, it can be harder to tell. Are these two things the same height? Well, it's kind of hard to tell when they're that far away. So what's going on there? The perceptual system that people have are really evolved to make relative judgments. It turns out we're not that good at absolute judgments. We might think we are, but what we're really good at is making relative judgments. And in many cases, the difference between those is not obvious to us. Um, so let's look at an example. Why does our accuracy of perceiving things increase when we have a common frame or they're aligned? So let's look at these two bars, A and B. Now, if I just ask you to look at A and B, it's a little bit hard to tell apart. Are these the same length? What exactly is going on? It's much easier if I actually encircle them in, if I've got a box, um, the same size box, that's the common scale. And then I can quite quickly tell that, B is definitely smaller than A. And if I align them, their position along the line scale is really, really easy to instantly notice that B is in fact significantly shorter than A. Why are these things not all equally easy? Um, well, this has actually been characterized as what's called Weber's law. So the ratio of an increment to the background is constant. Let's unpack that and see what that means. So what's going on with the filled rectangles is they're actually different by about 1 in 9. So that's not a completely easy perceptual judgment. It's not impossible, but it takes a little bit of thinking. The white rectangles, though, because of the common scale, these white rectangles are actually different by a factor of 1 to 2. So this is a really easy judgment. It's really easy to notice that this the right side white rectangle is twice as big as the left side white rectangle, whereas that's harder because the filled ones are 1 in 9, not 1 in 2. And then we're essentially doing a similar judgment when we align these. We're now able to actually check, is this one the same height as that, or is it a different height? That comes down to making another one of these um, judgments that have to do with how different is it. So here we see one example that helps us understand why alignment matters so much for our ability to accurately perceive length. Um, what else do we have to worry about? Well, color, by which I also include black and white perception. Um, so in this case, luminance judgments, this is one where we are really not that good at it. We think we are, but it turns out we're not. So let me ask you what might seem to be a really stupid question. Those squares here, A and B. So is A the same color as B, or is it a different color? It's a bit of a goofy question because it's a checkerboard. So, right, obviously they're not the same color. Um, But actually, I'm just going to take that same picture and put two strips of gray. And suddenly we notice, whoa, these are the same color. How could this be? Why do they seem so different here on the left side? It's because we've actually set this up so that one appears to be in shadow and one is not. The human perceptual system is doing a lot of work to try to automatically compensate for different kinds of lighting sources, sunlight versus moonlight versus artificial light indoors, things in shadow versus not, so that you don't stumble every time you actually have a shadow in front of you on a path. But what that means is then that our ability to judge whether two luminance values are the same or different, it matters a lot on what's next to them. So it's a very relative judgment. Similarly, if we look at colored things, here we see sort of a yellowish cast and a purplish cast on the same Rubik's Cube, and if we look at this, red subcube versus that red subcube, we can certainly tell they're both red. Just looks like we're wearing two different kinds of sunglasses. But again, if we were to actually just block these out and not see any of the other colors, so not have any of that context, then one looks much more orange and the other looks much more purple, because our eyes are used to doing this automatic color correction, which is great for living in the real world. It's tricky for visualization people that are ever trying to use color to visually encode. So we'll talk more about some of the complexities of color when we get to that unit later. The point I want you to think about for now is just remember that perceptually speaking, we're always making relative judgments, and we're remarkably not super great at making absolute judgments for color, for luminance, for length, for a lot of these things. Finally, before we wrap up, I just want to think a little bit about this question of how do you perceptually encode that things are related to each other by being in the same group? We've already talked about the idea that you could have a mark that would represent a link, whether it's containment or connection. And so clearly that's expressing some sort of grouping relationship. But that's not the only thing we can do. Even without having marks as links, we could perceive marks that represent items to be grouped together according to some sort of similarity in any of the categorical attributes. A really important one that has a lot of perceptual weight, is proximity. If things are in the same spatial region as each other, we tend to really strongly perceive them as being grouped together. Also, any of the other categorical attributes. If things are the same color, we think of them as grouped. If they're the same shape, we think of them as being in a shared group. So similarity judgments for any of the other categorical channels are also a way to express, again, at a perceptual level that doesn't require cognition, a way to express that things are grouped together. All right, a lot of this material, if you want to do more reading, is in the VAD book chapter 5, and also some things from Alex Lex and Mariah Meyer. All right, and I will now wrap up for this async lecture.